Welcome to the South Babcock Street Reconstruction Project.
I am Anton Saunders.
And I'm Diallo Farquharson.
And we are A&D consultants. The main sources we use to complete this project are the FDOT Flexible Pavement Design Manual, the FDOT Geospatial Map, and the Principles of Highway Engineering and Traffic Analysis 6th edition.
The design problems we faced were severe cracking, delaminations, and potholes. These poor conditions are not only harmful to motor vehicle components, such as tires, but also aesthetically unpleasant to their drivers, bicyclists, and any pedestrians traveling near the street. According to the Florida Department of Transportation's geospatial map, the road falls within the jurisdiction of Brevard County. Therefore, this county should be interested in addressing this challenge. We first identified a challenge that we felt applied concepts that were taught in the course. We then conducted a diagnosis by viewing traffic counts, traffic patterns, and collecting photos of infrastructure conditions. The diagnosis contains various elements that were useful in investigating the transportation challenge. Traffic counts have been utilized along with 18-kip equivalency factors in determining the 18-kip equivalent single axle load. Traffic patterns were identified so that the direction of traffic flow can be understood for design purposes. Infrastructure conditions were a key feature in the preliminary challenge analysis because the existing conditions that were observed provided the basis for the needed pavement design. Additional pictures are presented to aid in area identification and illustrate the current road conditions. CAD drawings will provide geometric information as well as road right-of-way boundaries.
This picture shows project engineers Diallo Farquharson and myself collecting data during our first site visit. The roadway layout provides an aerial view for purposes of displaying all elements in the vicinity of the road segment being analyzed. The traffic counts were obtained from the 2016 Florida Department of Transportation's traffic study of Babcock Street, 0.27 miles north of Nassau Boulevard. The data will be used for the construction of the flexible pavement design. Traffic patterns were identified so that the direction of traffic flow can be easily understood for the preliminary design purposes. The traffic patterns that affected the road segment the most were the north and south through traffic. This is because most of the traffic, specifically truck traffic, traveled along these paths, resulting in peak flow traveling occurring within these through patterns. The various turning lanes which existed within the roadway did not play as significant a role because most heavy traffic using Babcock as a through to travel to their final destination. The existing infrastructure conditions were identified during the second site visit. The existing roadway design was a flexible pavement design. Photos highlighting the various defects of the road segment were obtained for further investigations. One of the main issues identified was longitudinal and transverse cracking up to 2 inches wide along the entire roadway section, as seen in the picture. The cracks along the roadway could not be quantified due to the extent of their deterioration. It was determined that these cracks existed along the entire 0.24 miles of the South Babcock Road segment. Numerous potholes were identified and determined to be up to 3 feet long by 6 inches wide by 1 inch deep, as seen in the figures. Underlying soil sediment was observed, which caused uneven roadway conditions, as also seen in the figures. Delamination and the friction cause was evident throughout the north and southbound lanes. These conditions presented flood hazards for drivers as well as for pedestrians walking during a rain event. The photo shows the approach for the north direction. This photo shows the approach for the south direction. There, the north intersection at Bulldog Boulevard is seen. Lastly, the south intersection at Hibiscus Boulevard is shown. The computer-aided design drawing provides basic element descriptions and road right-of-way boundaries. The items borrowed from secondary sources are roadway layouts from Google Maps, traffic counts from the Florida Department of Transportation's geospatial map, and traffic patterns from Google Maps. The items developed by the team include the infrastructure conditions, additional pictures, and CAD drawings.
Issues to be addressed include safety, aesthetics, and constructability. As mentioned earlier, poor conditions are not only harmful to motor vehicle components, but also aesthetically unpleasant to drivers and pedestrians traveling near the street. The issue of constructability arose during pavement design. This was an issue because for constructability, it would be simple to produce a pavement design for both the South Babcock Street direction, which carries the greatest number of vehicles per day, and use it for the northbound direction. But doing this instead of considering the traffic in the northbound direction separately would incur a higher cost, because instead of accounting for the more economical design of the northbound lane due to its lower traffic volume, the heavy traffic flow of the southbound direction would be used at a higher expense.
We had to take into account the Brevard County typical minimum design standards. The solution to the problem addressed for the roadway segment is to implement a new flexible pavement design. The design approach follows closely to the pavement thickness design process for reconstruction in the FDOT Flexible Pavement Design Manual. It is as follows. Firstly, assume a structural number, usually around 4 or 5. Secondly, acquire axle load equivalency factors. Third, determine the structural number from equations 4.1 or figure 4.5. Fourth, check the assumed with the calculated structural number from figure 4.5 or equation 4.4. Fifth, if they are different, assume a new structural number and apply figures 4.5 or equation 4.1 again until you get the new calculated structural number. Step 6. Repeat all the steps until the assumed SN equals the calculated SN. Step 7. Calculate layer thicknesses and pick the material based on the calculated structural number. The southbound pavement design was calculated first. Multiple iterations were taken to acquire an accurate structural number value. Constants such as the reliability and standard deviations were taken from the FDOT Flexible Pavement Design Manual. The soil resiliency modulus was acquired from the state's material office. According to Table 3.1 of the FDOT Manual, reconstruction projects should be designed to withstand the 18 kip ES/AL traffic for 20 years. There are only 2 lanes on the roadway, so the directional design lane was calculated by multiplying the daily 18 kip ES/AL totals by 0.80 as per table 4.10 in the Principles of Highways Engineering and Traffic Analysis book. Here we have iteration 1 and 2, now the third, and now the final iteration. The same procedure for the southbound was followed for the northbound, and here is the final iteration. We wanted to compare our solutions from the empirical method with the graph-law method. The illustration will model the fourth southbound iteration. Having a structural number of 5.2 and a TSI of 1.7, a reliability of 90, and a standard deviation of 0.5, the W18 was validated. The individual pavement layer thicknesses were then calculated using the equation shown. 4 layers are being proposed for the design. It is assumed that a 12-inch stabilized subgrade, or LBR40, will be constructed. Using Table 5.5 from the Flexible Pavement Design Manual, the minimum structural course thickness and base group were acquired. Table 5.6 was then used to determine the base thickness and the material based upon Table 5.5. Lastly, a wearing surface material was chosen, and a layer thickness was determined by solving the aforementioned equation. The table shows a summary of the proposed materials and layer thicknesses to be used for the southbound and northbound lanes respectively. Finally, a CAD drawing was produced to illustrate the solution in the summary table.
The new pavement design will serve all travelers who commute on South Babcock Street daily, specifically those who work on or near this road. It will also benefit the clients both because of the reduced cost when compared to a concrete design and because of the north and southbound specific designs. The first benefit is for drivers and pedestrians because when poor road conditions exist, drivers have a tendency to swerve on the roadway in an attempt to avoid damage to their vehicle. This action can be dangerous to other road users who must account for a vehicle possibly entering their lane unexpectedly. The second benefit is the enhanced roadway aesthetics for drivers, cyclists, and pedestrians. This is important in improving the serviceability of the road because travelers are more inclined to travel on good-looking, smooth roads. The third benefit is a reduction in energy consumption by reducing the resistance which is caused by the deteriorated roads. The fourth benefit is the elimination of potholes which cause vehicle deterioration. In summary, the challenges addressed were severe cracking, delamination, and potholes. The key elements of the diagnosis were roadway layouts, traffic counts, for analysis, constructability, for the solution, flexible pavement design, for the benefits, pedestrian and driver safety, reduced vehicle deterioration, and energy consumption. Any questions?